We're talking about charge here. We have a fair amount of experience handling charge related phenomena in our everyday lives. For example, we've all experienced this, that sometimes when we are wearing synthetic clothes on windy and dry kind of days, when we touch a metallic object, we feel a bit of a shock, and electric shock actually, and we never really can imagine that either we or that object was connected to electric supply, and yet we experience a very small shock. Sometimes when it's dark, we can even see a spark flying from our finger into that object. There are also a whole lot of other experiences, observations of nature. For example, lightning strikes happening, they are charge related. Lightning strikes actually dump enormous amounts of charge into the earth. Then we have these observations during winter when we are using those synthetic blankets. If we rub them against each other, we can see sparks flying, especially if it's dark. We can see sparks between sheets of synthetic blankets. All these are charge related phenomena, and people have been observing such phenomena since very long ago. Even the ancient people made such observations, and such observations by ancient Greeks are documented and so on. So charge related phenomena are all around us. But then what is this charge? How do we describe it? How do we define it? Well, when in ancient times people started observing charge related phenomena, they made certain observations about certain types of objects. For instance, when a glass rod is rubbed against a silk cloth, they both acquire charge. So a silk cloth, it's being rubbed against a glass rod, and both the silk cloth and the glass rod acquire charge. Now, how do we know they have acquired charge? Is that if we have two of these glass rods which were charged in this manner, and we bring them close to each other, we can observe that they tend to repel each other like this. So they tend to move away from each other because of the repulsive force. Similarly, if two such silk cloths are brought close, they tend to repel as well. And if one of these pieces of silk and a glass rod charged in this manner, when they are brought close to each other, they appear to attract each other. Now, the ancient people who made these observations for the first time, they kind of assumed that because we rubbed these objects against each other, they got angry, and the word charge has connotations of anger in English language. Also in Hindi, we call charge avesh. Charge is called avesh in Hindi, and the word avesh directly means anger. So the word charge has connotations of anger, as if these objects, when they were rubbed against each other, they got angry. So they acquired this property of anger, these objects. Now the ancient people, they made this observation that when two objects of different kinds are rubbed against each other, they acquire a property of charge which to them seemed to resemble anger in some sense. Now, they also came up with another conclusion here, going by the same experiment. They made an assumption that there must be two different kinds of charge. So when a glass rod is rubbed against a silk cloth, they both acquire different types of charge. The glass rods acquire one type of charge and the silk cloth acquires the other type of charge. And so when the glass rods are brought close together, they repel. And similarly, when the silk cloths are brought together, they repel as well. And therefore the conclusion was that the same kind of charge repels. So they came to this conclusion that like charges repel. But then when the silk cloth and the glass rod are brought close together, they appear to attract each other. And because they attract, it was assumed that different types of charges or unlike charges would attract each other. So the ancient people came to another conclusion here, that unlike charges will attract and like charges will repel. Also, they developed a notion of positive and negative charge as well. When a charged glass rod and a charged silk cloth, they were put together and kept together under slightly moist conditions. Then after a little while, an observation was made that they stopped attracting and repelling, etc. So this property of charge that they had acquired vanished. And therefore, they kind of concluded that the two different types of charges must have a nature of positive and negative numbers. And when those positive and negative numbers are added, equal positive and negative numbers, if added, give us a zero. So that's how charge on these two bodies would disappear if they were brought in contact and kept in contact in moist conditions. So they had a notion of positive charge and negative charge. This notion existed even before we knew of matter being made up of atoms and protons and neutrons and electrons. So the discovery of charge dates back to a time well before the structure of atom was known in any way. And therefore, charge was known to be positive and negative. This was understood. It was understood that like charges repel and unlike charges attract. So we'll be doing a little chronicle on how these properties of charge got discovered. The first property that was discovered was that there are two types of charges. Positive and negative charges. And it was understood by this time that like charges repel and unlike charges attract. Now, this was understood well before the structure of atom became known. Now later on, once structure of atom was better understood, then it was realized that matter is made up of positively charged protons and negatively charged electrons. Each proton and electron carrying the same amount of charge, but the protons carried positive charge and the electrons carried negative charge. The amount of charge on both was known to be equal, and it was also understood that as a whole matter is electrically neutral. Now, Why was matter known to be electrically neutral? Because under normal circumstances, matter objects, like for instance these two objects, do not attract or repel each other. Since they do not attract or repel each other, we can safely assume that they carry no charge. So matter as a whole was assumed to be made up of equal amounts of positive and negative charges. So matter is electrically neutral as a whole. But then that's under what we would call normal circumstances. Now when two objects are rubbed against each other, we understand that some electrons from one object can get transferred to the other object. Now any object will have the same number of electrons and protons, and therefore the net charge would be 0. But when we rub two objects against each other, one donates its electrons to the other, and the donor acquires a positive charge, and the gainer of electrons would then acquire a negative charge. So if we have two objects rubbed against each other, acquire charge by exchanging electrons. So suppose we have two objects, we have A and we have B, and A donates n electrons to B. Now when A donates n electrons to B, the charge that A will acquire will be plus n times the charge on an electron, E being the charge, the magnitude of charge on an electron. A will acquire charge plus Ne, and B will acquire charge minus Ne. So when two objects are rubbed against each other, there will be an exchange of electrons. The one that gains electrons gains a negative charge. The one that donates the electrons develops a positive charge, because originally it had the same number of electrons and protons, but now that it has lost some electrons, it has more protons which are positively charged than the negatively charged electrons, and therefore the net charge acquired by A is positive, the net charge acquired by B is now negative. So the charging mechanism between two objects is through exchange of electrons. Another interesting thing that we can easily observe here is that charge is quantized. Now what is the meaning of this term, charge is quantized? When we have a physical quantity which can only take on certain specific values, certain discrete values, then we say it is quantized. But then you would say that that's Greek to us. What is discrete values or special values? So let's take up a simple couple of examples to understand this term quantized. For instance, if you hire a taxi, let's say the fare starts at ₹100 and then it increases in 5 rupee changes or 5 rupee increments after every half a kilometer, let's say, for example. So the fare or the bill of a taxi ride can be 100 rupees or 105 rupees or 110 rupees, 115, 120 and so on. You can keep adding 5. But the bill of a taxi ride cannot be 86 rupees. It cannot be 102 rupees 25 paise. So it cannot be 102.25 in currency units. It can be 100 or 105 or 110 or 115 and so on and so forth. So the bill of a taxi ride is quantized because it can only take on certain specific discrete values. Those special values which are permitted would be called permitted discrete values, and this phenomena, this kind of special values being permitted for a particular quantity is described by the term quantization or quantized. Any physical quantity which can only take on some special or discrete values is said to be quantized. In case you have studied, for instance, Bohr's model of the atom, you might have also studied that the energy of an electron in an atom can only take on certain special values. So in the Bohr hydrogen atom, in the first orbit, the energy of the electron is minus 13.6. In the second one, it's minus 3.4. In the next, it's minus 1.51, and so on and so forth. So only certain special values of energy are permitted for electrons in the hydrogen atom. So those are discrete or special permitted values. And when a quantity is permitted only certain special discrete values, we say it is quantized. So the energy of electrons in the atom is quantized, and similarly the charge on an object has to be quantized. It has to be an integral multiple of the electronic charge. It can be plus or minus depending on whether the object is a net donor of electrons or it's an acceptor of electrons. For an acceptor of electrons, the charge will be negative. For a donor of electrons, the charge will be positive. But it will always be an integral multiple of the charge on an electron. This n, of course, has to be an integer. That's 0, 1, 2, 3, and so on and so forth. So this is what we mean when we say charge is quantized. Another interesting thing about charge is that charge exists with mass. Charge will always exist with mass. It will never be there without any mass. So, what kind of particles have charge? You have electrons, you have protons, and these particles will always have their own mass, and therefore electrons, charge in general will accompany mass. Without mass, there can be no charge. So charge always exists along with mass. It cannot exist without mass. And another interesting thing about charge is that charge is invariant. Now, what is invariant? In Einstein's theory of relativity, the mass that an object possesses would be observed to be different for different observers. So if an observer is looking at an object, for instance, I'm looking at this marker pen, and to me it appears to be at rest, and now if I make measurements of its mass using whatever experiments, the mass that I will observe is called the rest mass, because with respect to me, this object is at rest. And when some other observer looks at the same object, but for that observer this mass is moving with some speed v, then for that observer the mass that's observed will be higher, will be larger. We are not going into that theory of relativity here, but if m0 is the rest mass as I just described, then the mass of the object as observed by an observer with respect to whom this object is moving with v0, then the observed mass will be measured as m0 by under root of 1 minus v square by c square, where c is speed of light or velocity of light in vacuum, and v is the speed of the object as observed by our observer. So mass becomes variant. Mass is a variant. It varies with the velocity of the observed object, but charge is invariant. It does not vary when the velocity of the charged object changes. And here you will notice that when velocity increases, mass increases as well. And when the velocity, of course, approaches c, the velocity of light in vacuum, then v square by c square becomes 1 and the observed mass approaches infinity. Now, since mass increases with velocity, with increase in velocity, specific charge decreases. Now, what is specific charge of an object? Specific charge is the ratio of the charge with the mass. So charge to mass ratio, that's your specific charge. It decreases with increase in speed. Specific charge decreases with an increase in speed. Why? Because when speed increases, the observed mass m increases, and when m increases, q by m decreases. Remember that q, the charge, remains unaffected with change in the speed of an object. Is that charge is a scalar and also additive. Now, what does that mean? Scalar quantities are those that do not have any sense of direction, and charge, of course, does not have a sense of direction, and therefore it is a scalar quantity. And with scalars, we all understand one simple property, where it can be simply added or subtracted like regular numbers, and therefore it is additive in nature. So if we have two objects, one object carries plus 10 units of charge and another carries minus 4 units of charge, if we bring them in contact and they share their charges, the total charge will be on the final larger object, the total charge will be the sum of the original charges. So we had plus 10 units and minus 4 units added together, they give you 6 units of charge. So charge is a scalar quantity and it is an additive kind of a quantity. You can simply add charges on objects to get their total charge. Add, of course, like regular numbers. Now, another interesting observation about charge is that charge of an isolated system is conserved. Now, what do we mean when we say charge of an isolated system is conserved? What we really mean to say is that if we have an isolated system, now that's a system which is not exchanging any matter with the surroundings. Now for such a system, for a system that's not exchanging matter with anything outside the system, that's an isolated system. For such a system, the total charge on the system will remain constant, will not change, cannot change. And that's conservation of charge, which is a very, very fundamental conservation law, which is in fact more widely applicable than even conservation of mass. Actually, mass is not even conserved in a whole lot of physical phenomena. Like for instance, in nuclear reactions, it is quite normal to see mass being converted into energy or energy getting converted to mass. Both possibilities exist in nuclear reactions, whereas with the charge there is always a conservation. So even in nuclear reactions, charge is conserved even though mass is not, and therefore the total charge of a system will always be conserved, will remain constant, and that's the law of conservation of charge. Not going too much into this as of now, but it will be applied in a whole lot of practical kind of applications, which we will take up later on in this chapter. So charge of an isolated system is conserved. Now these then are some properties that charge possesses. The next discussion now is how do objects acquire charge. Now we've already seen one method of acquiring charge, that is the method of rubbing. The methods of charging. How can objects acquire charge? The first is charging by friction. Now, we've already seen that when two objects are rubbed against each other because of the force of friction between them, the objects can get charged. Why this happens really is because different materials have different magnitudes of work requirements for extracting electrons from them. So say for example, a material A requires a certain amount of work to be done so that an electron can be extracted from its surface. Now let's name this work requirement as work function. So work function is the minimum work that is required to be done to extract an electron from the surface of an object, of a material. Now when we are rubbing two materials, two objects against each other, now these objects are made of different materials, and since they are made of different materials, they have different work functions. Now the object which has the lower work function will lose more electrons, and the object which has greater work function will lose less electrons. So if I rub these two objects against each other, and let's say this one has the lower work function, this will lose more electrons. This object will also lose its electrons to the other object, but this object will lose less electrons while this object will lose more electrons. So in the end what happens, the marker gives more electrons to my hand than my hand gives to the marker. So the marker is a net loser of electrons. The marker has lost electrons, whereas my hand has gained electrons. And as a result, the marker has become positively charged and my hand has become negatively charged. So always remember that when two objects are rubbed against each other, when two objects are rubbed against each other, the one with lower work function acquires a positive charge, and the one with higher work function acquires a negative charge. So I've explained this mechanism of charging by friction now. Now this is not the only way things can get charged. There are other methods that can be used in charging up objects. The second process is charging by conduction. Now, very briefly, let's define a conductor. A conductor is a material in which electrons or other kinds of charge carriers can move freely. So, in case of conductors, the movement of charges on the object is completely free, the unhindered movement. And this happens more frequently in metals than in other materials. There are of course electrolytes which can conduct as well. But in our physics classes we'll generally tend to focus more on metallic kind of conductors. Now in metallic conductors there is free movement of electrons and therefore there is free movement of charge, and therefore we call them electrical conductors. Now these electrical conductors can easily exchange charges with each other. Now suppose we have two conducting objects, A and B. Now they're both conducting objects. A has some charge, let's say plus Q, and B has no charge on it. Now if we connect them by a wire or we bring them in contact, what will happen is this charge Q will get eventually shared between them. So let's say A has a charge Q1 now and B has a charge Q2. It's that same amount of charge Q that has now been shared. Of course, the total charge of this isolated system will be conserved, so Q will be equal to Q1 plus Q2. That's your law of conservation of charge applied here. Now the charge has been shared. Now even if we disconnect, both bodies will continue to carry these amounts of charge, and so this uncharged body, which was uncharged initially, has now acquired charge. These acquired charges will be of course equal if the charged body, if these two bodies are identical in shape and size, then they'll acquire equal amounts of charge. These charges can be different for bodies having different shapes and sizes, but in case they are identical objects, the sharing of charge will be identical. More on this in the later chapters on electrostatics, but do remember that conservation of charges applies here, and therefore the total charge on these two will be equal to the original magnitude of charge. And this describes your charging by conduction. Now there is another method of charging, and that's called charging by induction. Charging by induction. What is charging by induction? Induction is kind of it's a word used to express the fact that things can be influenced from a distance, and influencing from a distance is what we call induction. So when an object can acquire charge because of the influence of another charged body without coming in contact, we say this is charging by induction. So in conduction, charging by conduction, what was required was that the two objects got into electrical contact with each other. That is, they were brought in contact or connected by a conducting wire. In induction, we require no such thing. They do not need to come in contact. They do not need to be connected by a wire, and yet charging can happen. And this is what we call charging by induction. Now let's see how this can happen. Suppose there is a charged body A, and it carries some positive charge on it. Now over here we have an uncharged object. Let's call it B, and this is a charged object. Now what happens is, after all, this object B is made up of matter which contains positive as well as negative charges. What is going to happen now is that the positive charges in this matter, in this object, will be repelled away from this positive charge. So this positively charged object pushes the positive charges in B away from it, and therefore positive charges tend to accumulate on the far side of the object. Now, since this object had no charge on it, and this side has acquired positive charge, on this side it has to now acquire a negative charge. Of course, both are equal and opposite. This object remains an isolated system as of now, and therefore the charge on it before the event and after the event remains zero. So it initially had zero charge, and it still has zero charge because these negative and positive charges are equal. Now what can be done quite easily is that this A is kept here, it doesn't shift anywhere, whereas now with B what we can do is we can perhaps connect B with the earth, or a B can be connected with any other object. Now what happens, because of repulsion from this positive charge, this entire positive charge over here will escape into the earth because of repulsion. And now even if we remove this body retains this negative charge on it, and therefore body B has now acquired a charge due to the influence of body A without any contact, and this kind of charging we call charging by induction. Now before we can proceed further with this chapter, just a couple of important facts that you will need to remember. The first one of them is that the unit of charge is called Coulomb. That's the SI unit of charge, and It's a very, very large unit of charge. In fact, a charge of 1 coulomb is almost impossible to accumulate in one small location. It's a huge unit, and therefore practically the unit of charge that's likely to be used would be microcoulomb or picocoulomb or nanocoulomb. And interestingly, it's pronounced coulomb with a silent B. It's coulomb and not coulomb or something like that. So it's a unit of charge. The other thing we need to remember is charge on an electron. We describe it as E, and it is minus 1.6 into 10 to the power minus 19 coulomb. Now that's a tiny amount of charge, but then matter is made up of some enormous numbers of electrons and protons, and therefore the total charge on a given object can be significantly large, even though the charge on one unit, that's like if we take electronic charge as a unit of charge, then this is a very tiny unit. This is a very tiny amount of charge. But typically matter contains atoms of the order of 10 to the power 23, and so the numbers of electrons and protons available on objects are of the order of 10 to the power 23, and therefore objects potentially have the ability, matter has the ability to acquire very large amounts of charge, although they are very difficult to concentrate on small objects. But matter does have the ability to acquire significantly large amounts of charge. This then is the initial discussion on what is charge, also what are the methods of acquiring charges. A couple of interesting observations here, and that is, you recall the interesting fun you used to have when you were small children. You would rub a foot ruler, plastic ruler, in your hair, and you would attract tiny pieces of paper with that ruler. It's a common experience. We all did this as children, and I'm sure all of you have also done it at some point of time. That phenomena comes from here. This is charging by induction. Now when you rub your foot ruler in your hair, it acquires charge. Now it may be positive, it may be negative, it's a different issue. It acquires charge, and then what happens is pieces of paper acquire charge because of the presence of this charge. So let's say, for instance, the foot ruler has a positive charge on it. The near surface of the piece of paper acquires a negative charge, and the far surface acquires a positive charge. Now the attractive force on the negative charge will be larger than the repulsive force on the positive charge because of distances. The negative charge is closer to the positive charge, so it experiences a larger attractive force than the repulsive force experienced by this positive charge. So over here, this positive charge is experiencing a small repulsive force, say Fr, and the negative charge here is experiencing a strong attractive force. Now this force being larger, there is net attraction of the object by this positively charged body. So this is what explains the attraction of those pieces of paper with a foot ruler. And therefore we also need to remember a very, very important idea, that two objects can attract each other even if only one of them has charge on it. The other object acquires induced equal and opposite charges and can still feel an attractive force even though the net charge on the object remains zero. As a result, repulsion between two objects, strong enough repulsion between two objects, confirms that they both carry like charges. But attraction between two objects cannot confirm that both objects are charged. Attraction can happen even when only one of them has charge. Another very important thing that you will need to remember is that when you have charged objects placed in each other's vicinity, and there are other bits of matter around, then that matter can also acquire induced kind of charges, and that matter then starts affecting the forces, the net kind of forces which the objects experience. Therefore, the law that governs forces between two charged objects gets slightly modified when the charged objects are placed inside matter. So let's say inside a medium, inside material medium, if you place charges, the forces are kind of modified, and we will be talking about how exactly that happens. So these are the basic properties of charge and also the methods of acquisition of charge. In the next session, we will be discussing about the forces between charged objects.